Okay, all right. So thank you for the kind introduction. I think I will not further self-introduce. I'll just say, hi, I'm Tamara. Thanks for coming here on Friday. Been doing this for quite a while, these days at UBC. Um, and let me talk about my current obsession. So the title of this talk is Marx Revisited Beyond Bertin. And let me talk about what's going on with that. So first of all, I have co-conspirators. My name was the one that was on the slide, but I've actually been talking with a number of people about this. This work perhaps someday will become a paper. And so Richard Brath of Uncharted Software, some of you might know that as Oculus in the old days, has been working a lot on this with me. And three folks from UBC Computer Science who have been TAs in my InfoVis course several times, Mara Solin, Francis Nguyen, and Marian Smith. I've also talked to a lot of people, including Northeastern's own Enrico Bertini, and Hans-Peter Pfister, and Arvind Zajranian, and Maureen Stone, and Martin Wattenberg about some of these ideas, and their ideas have then gone into the blender of my mind and changed how I think. So although I'm not individually attributing things, there's been a ferment of talking with folks about this for a while. So what is Marx and channels? It's a foundational model that people have been using to think about visualization theory with for quite some time. So the big idea is if you've got some visual representation of data, let's call that a visual encoding, you could break that down into marks and channels. And by marks, I mean geometric primitives that represent items of data. And by channels, I mean ways to control the appearance of those geometric primitives, those marks, to try to represent data, whether it's with position or color or shape or size or orientation. So these are ways to visually encode data. So this is not a new idea. It's a very, very old idea. It goes way back to the 60s. Jaques Bertin's Semiology of Graphics is a foundational text that has inspired a lot of thinking and visualization. So this model goes all the way back to people have done a lot of thinking about things like, well, how do you pick which channel to use? And they've come up with rankings that are very perceptually based, where we think about things like the expressiveness of how the information is processed by your visual system. And so there's matching of data with channel capabilities. Like, does your perceptual system interpret this as an ordered thing, a magnitude, or as a category, as an identity thing? There's effectiveness, like how much can people decode from the picture that you tried to encode as the designer? So the accuracy of the human's ability to perceive information encoded according to these channels. A lot of that work dates back to Cleveland and McGill's very foundational work on two value ratio judgments about how can you decode. Okay, so in this talk, I'll go into a little bit more detail about this model, and then talk about why it is that when you try to teach this model, it's actually trickier than you would think. And maybe there's some structural barriers in terms of just using this as a help to reason. And so I've got some ideas towards alternatives, which I will talk through, and then with luck, do some debate and discussion. So what is this model? I told you about the basics, but how do we use it? So the idea is, confronted with some visual encoding, you could decompose it into marks and channels. So analyze the structure of what I'll call an idiom. You could call that a technique or a chart type or something like that, as some combination of marks and channels. So I don't think these are new idioms to you. You've seen bar charts and scatter plots before. When we analyze them according to this model, we say, oh, we're encoding with this channel of vertical position. We seem to have a line mark. Or, oh, we're now using a point mark. We can encode with vertical position and horizontal position separately. That gives us a standard scatter plot. Oh, we could color code that scatter plot. Now we're encoding one more attribute. We still have a point mark. Oh, we could size code those things. We still have point marks, but now they're size coded. So far so good. These are common statistical graphics. There's probably not a lot of new ideas here. So where does this break down? This is the model so far. Well, okay, this was tabular data. So this is sort of common statistical graphics. We're going to treat a simple table where the data items are the rows in the table, the columns of the table are what we're going to call attributes, and those are the things that we're encoding with the visual channels. Well, what about spatial data? Oh, this model still works. So very common to use, for example, choropleth map. We're saturation coding, that is color coding, these geographic regions. So that means we've got an area mark. We're using color channels and also, well, seem to be somehow using position. What about network data? Well, now we don't just think about items of data, we also think about links. So these are often called node-link graphs, these networks or these trees. So we can connect up to items together with connection marks. We can use a containment mark that uses enclosure or nesting to communicate hierarchical structure. So it's very common to show these things with node-link diagrams, which is where we're actually using points for the items or the nodes and a connection line between them. Or we could say, let's show hierarchical structure with containment. That's this tree map approach where you have an area representing a node and you contain to show that parent-child structure rather than showing it as a connection mark. Okay, so why are we doing this? Now, what we're really doing is we're trying to have this model of decomposition we're really using this as a design space. So what's a design space? It's something where we want some power to describe. We want to describe, first of all, a good range for the things we care about, and we want to be able to discern between categories that we think of as different. So we want descriptive power. We want evaluative power. We want a design space to help us say, given a bunch of alternatives, which one's better for a particular context. We want generative power. We want to be able to say, hey, I'm making a new design. Does this help me think? And these criteria from Michel Bottin-Lafont, they're criteria I'm particularly fond of thinking about. Now, this word design space, people use many different words when they're talking about this general class of ideas. Sometimes they call it a taxonomy or a typology or a classification or a framework or just plain the model or a grammar. For our purposes, I'm going to treat all of these together. I'm just going to say this is this way of helping us think. And the reason it helps us think is we delineate the categories we care about. We often call these dimensions or axes. And what we want to do is have these be as independent as possible from each other. We want these to cross-cut so that then we can reason about things. And in particular, we want a structure that's both systematic and actionable to help us make decisions about, for these possibilities for a particular problem, what might I do? So we want to reason about design choices. We want these axes to capture the important things, the key variables at play. And I really love this way of framing it from Paul Ralph out of software engineering, who says we can use them to increase our cognitive efficiency because when we group similar instances together, we can reason and make inferences about the whole group instead of instance by instance starting from scratch every single time. So they give us a way to tackle our cognitive territory. So thinking about design spaces and visualization, well, the short answer is people have been using these for a long time. It's a continuing theme from the past to the present. Cardin McKinley had a very influential early paper on the structure of the design space of, always visually encoding data. Javid and Elmquist thought about the design space of how to have composite visualizations. Schultz et al. Thought about the design space of visualization tasks. A recent paper from Elliott et al. Is the design space of vision science methods for even doing research. So you can have a design space of almost anything. So design spaces are something we use a lot in visualization. I myself think a lot about design spaces because I wrote a book about, at this point more than 10 years ago, visualization, analysis, and design. And basically you can think of that whole book as one big giant design space of here's visualization, here's how to think about it. I'm currently engaged in thinking about a second edition of the book, and thus everything is up for grabs again about, what should it be? Do I like the old one? So how do you visually encode data? How do you interact with a single view? How do you chop things up between views? How do you reduce the amount of data to show in a view? So as part of thinking about this design space, I've gotten quite fixated on this question of the marks and channels part of it. How do you encode data? So, why am I so fixated on that? Well, I decided I wanted to teach with these design spaces. So, you say, given a visual encoding, let's try to understand the relationship between that and some data set. So you could have a homework assignment, non-hypothetically, of analyze an existing encoding with this marks and channels approach. So you say, what visual channels are used? Here's a picture. What channel is used to encode what attribute? What kind of mark is used to encode what kind of data item? It seems all very straightforward. The reason we're doing this is the idea that if you learn how to reverse engineer an existing design, it'll help you when you're generating a new one. So this really is to try to get you fluent with the principles of visualization. Analyze existing in order to generate new better in the future. So Enrico Bertini to the rescue. He also has taught many visualization classes around the framework that my book is framed around, and he developed some great in-class exercises to help students do this. And I thought, fantastic, I will steal Enrico's exercises, I will use them, I will declare victory, and the world will be great. So I did the first part. I stole his exercises and I started using them in class. And it was amazing what I learned did and didn't work. I thought I literally wrote the book. How hard could this be? And there were many, many, many questions that were very tricky that I found quite hard to answer. So what was going on here? Why was this so complicated? I made a bunch of my own. I went out into the world, snagged a bunch of interesting visualizations. So let's start out with a relatively easy one. Let's grab this one from Mona Chalabi of The Guardian. And she made this very trenchant graphic pointing out the difference between the number of shootings and the amount of press coverage of those shootings according to the race of the shooter. So let's start with a basic idea of mark type. What's going on? In this grouped bar chart, what is the mark type? How many people think it's points? How many people think it's lines? How many people think it's areas? How many people don't know or don't care? Okay, so, what channels are we using? We seem to be using position, there's some color coding. Well, so about length versus area, how many people think this is using length to code? How many people think this is using area? Okay, so a lot of consensus on that. How many people think it's angle? Nobody. Okay, so that wasn't so bad, except for what it tells us about our society. But from a visual encoding point of view, not so bad. All right, so what about this one? New York Times graphic about corporate taxes in the US. So how many people think that the mark type is point? How many people think it's line? How many people think it's area? How many people are completely confused? Right. So this one's a little harder. It's not quite so clear. Clearly we're using spatial position, at least horizontally, to mean something. We're color coding. Maybe somehow we're using size to communicate something here. So what is going on here? How about this one? There's stuff on the screen. What is that stuff? Is it points? How many people think we've got point marks? How many people think we have line marks? It looks like a bar chart, doesn't it? How many people think they're area marks? How many people wonder what's going on? Yeah. So what in heck is happening here? So somehow what seems to be a very straightforward exercise generated a great deal of questions. And, one thing we could consider is, well, maybe this is just a bad idea and we don't need to do it. Why analyze visual encodings? But I think there's value in that. Or maybe you'll say, well, maybe mark types is not important. Maybe we don't need anything. But actually it turns out that marks is a useful framing of things. What I take is that this is evidence that this design space could be improved. Maybe there's a better way to think about this sort of thing that might help us reason more effectively. So one thing to notice is everyone writes papers about channels. This is heavily studied. There are, hundreds of papers trying to characterize our ability as humans to look at pictures and, decode information from them. So quite a lot of work, both replicating and extending and refuting and arguing against these ways of ranking channels. What about the poor mark? It's kind of ignored. The mark part of the model, just nobody ever really talks about or thinks about. We just inherited this. It goes all the way back to Bertin. And the thing is, it just seems like there's nothing to argue about because after all, geometric primitives are dimensional. Points are zero-dimensional, lines are one-dimensional, areas are 2D, volumes are 3D. How can you argue with this? It's math. What is to argue about? Well, so first of all, before we start arguing, let's think about the limits of this analysis. What's it for? What's the context we do it in? Why do I even care about marks? Well, one thing is it's really nice to think about the scope of when you've got one mark for one item. That's a constrained world. So what are the two other ends? Well, what if you have a lot of marks for one item? You might have something we call a glyph, where you try to actually construct with a bunch of different marks something that tells you about this. So here's a glyph from an Eamon McGuire paper that's about, biological flow processes, where you've constructed a glyph out of a bunch of little submarks. Or maybe you're using multiple views. Maybe you have two views side by side where the mark is represented in one way in one of the views and in another way in the other view. Or maybe you have two views on top of each other superimposed as layers, using layering. So that's where you have multiple marks for one item. Well, what about the other side? What if we have one mark for a bunch of items? Maybe we're aggregating. Maybe we have one mark representing a bunch of items as a proxy for them all. Maybe we're filtering where we've just plain decided not to show some of the marks because they're not crucial for the part of the analysis we're doing now. So we can actually think about the world in which there's one mark per item as a useful microcosm to reason about. It often corresponds to a single window. And that is a useful unit of analysis. And that's one reason I want to continue thinking about things at the mark level. It gives us a scope to think. The other thing that we're thinking about is what kind of a model is this? And for a decoding model. And I already alluded to the idea of encoding versus decoding. So what I mean by that is marks and channels has been very much an encoding model that's trying to help a designer make decisions. So it's a prescriptive model. It's providing guidance for design. It's aimed at the person doing the encoding, the visualization designer. But the flip side of that is the decoding, which is that the viewer of visualization, something is happening with their eyes, with their brain. They are decoding that information. And how will they interpret it? And, the short answer is it's complicated. But we do have some predictive models that are typically built on a lot of work in vision science and perceptions. And coming out of psychology, there are some models for what's going to happen when you decode. It's not necessarily, so there's a lot where we don't know. There's a lot we do know. There might be multiple possible answers depending on who's doing the looking and what context they're in and what they've been up to lately. The point I do want to make is decoding is not the same as reverse engineering the encoding. So this exercise I'm asking students to do of figure out what the designer was doing. That's not what most visualization viewers are doing. They're just interpreting. They're just looking at the picture and trying to understand something. So I'm really distinguishing between reverse engineering the encoding and a full-on model of what humans do when they eat. So the interesting question, of course, comes, when do these not match up? So let's look at a much beloved and sometimes hated thing, the pie chart. What's going on with pie charts? And so this video is, well, what are we doing here? So we seem to have area marks and the channel seems to be angled and we've constructed this sector-like wedge and the two-dimensional area varies. Okay. So, right, and we go along and we have a radial ordering and the length of each of the wedges is uniform. They go all the way to the edge of the circle. Now, we know a bunch of psychological theory that tells us that we are less accurately able to decode angle than rectilinear position. Okay. So in that sense, they're sort of similar to bar charts, but maybe we can't do things at such high precision. But what's going on when we decode? Well, there's some really compelling papers by Robert Cassara, who then went off to Tableau, that it's almost certainly not angles. That even though you encoded with angle, if you wrote the code, you could actually write code that uses angle to make that picture on the screen. But what human eyes and brains are probably decoding, most likely it's art length. Maybe there's a bit of area involved, but we know it's not angle. So there's a bit of a discrepancy. Okay, good to know. But maybe one's a good proxy for the other. Maybe we can still reason about that. If you want to hear more about that, there's a nice blog write-up, a whole series of papers. Okay, what about another idiom? What about the coxcomb chart? Sometimes this is known as the nightingale plot or a rose diagram. This is actually a more direct analog of a bar chart. So what we're doing is we're encoding marks with the length of channel instead of with that angle width channel, so that the length of the mark is varying. We're still going around radially, and the width is uniform instead of the length being uniform. So it's really more a direct analog to a radial bar chart. So what's that mark type? Is it a line because you length coded? Is it an area because the area is varying? What's going on here? So let me draw some annotations on this. What we've got is, you could say, well, literally, again, if you wrote code to do this, whether in R, D3, Python, whatever, you could actually say, well, we're encoding a length. That's a number. But what you're perceiving, what you're decoding, is most likely two-dimensional area. And here's the problem, is that's not uniform. So as the length increases, that area is increasing in a non-uniform, non-linear way. So that variation is not really doing the same thing in the length as in the area. Whereas in a bar chart, it's pretty safe because the width is uniform. So that area is linear with the mark length instead of non-linear. And that's one reason that people can get confused with these charts more so than with a straight bar chart. So and notice that this is not about radial versus rectilinear. you can have a radial bar chart where there's a uniform width. So this is not about the layout approach. It's actually about more fundamentally this divergence of models. So we've got a divergence of encoding and decoding. And well, what if the two different channels tell you different things? Which one wins? That's a difficult question. So that's one thing to think about, encode versus decode. Now let me get to the new stuff. So what do I want to do that's different? So what I want to do is I want to think fundamentally about constraints. And what if we conceptualize both marks and channels as imposing constraints? So, for example, could a mark type impose some constraints on what channels are available for use? Could using one channel constrain what you can do with another channel? So how can we think about this? Well, for one thing, let's start by saying, what do I even mean by use? What does it mean to use a channel? So let's take another non-hypothetical example of an exercise for students where you ask the question, does channel size encode an attribute? This is a visualization stolen from Tableau Public. So what answer could you say? Well, you could say yes, because look, the sizes are different. And then when I say, well, what's it encoding? You could say it's the dog name in alphabetical order. That's what it's encoding. Now, do we like that answer? A different answer is no. The size difference doesn't mean something. It's not fundamental to the data set. It's a complete artifact of the fact that you chose a radial layout. And if you'd laid out that grid rectilinearly, all those boxes would be the same size. So fundamentally, no, it's not a good answer to say that. It's not a real attribute encoding. Fine, you could derive that and you could argue that, but maybe there's something that's not satisfying about that answer. So maybe a different way to say this where the answer is a bit more obvious is, if I wanted to augment this visualization by adding another attribute and using another channel to put more information in here, could I use the size channel without obliterating what you see in this chart? And the answer is no, that's a terrible idea because size is already varying because of the radial layout. It's not a freely available channel. So, it would change the meaning of the chart if I tried to now size code some other attribute with that. So it would change the meaning of this graphic in a pretty fundamental way. So let's call that an unavailable state. The size channel is unavailable. So this makes me think about, well, maybe we should model channels according to, well, are they encoding data directly? So is there an attribute that actually has a semantic meaning in the data set and it's clear? And of course, remember, you might have more than one channel that's being used for the same attribute of data. You could redundantly encode. Or is the channel free? Can we add to the visualization without obliterating its meaning? So let's call that free. Or is there some way in which a channel is unavailable? It's somehow taken. It's not really free anymore, but we're not really directly encoding anything. So let's call that unavailable. Now, could that be because of the mark type? Could it be because of the very particulars of how your idiom works? Could it be because another channel is somehow using it up? So let's think about that. So let's rethink, in fact, about some of this. So this idea of an area mark, I argue it's a terrible, terrible name. Why? Well, for one thing, all the marks have area. If you think of graphical area, well, you could color code a point, you could color code a line, you could color code an area. So these are not mathematical things, right? Points are not actually zero-dimensional. If you were doing computer graphics, you would be drawing them all as polygons that can be colored in or textured or doing any other thing with it. So from a kind of graphics frame of mind, these are all just polygons. Now, so there's an area mark and there's an area channel. Are those the same? Oh, no. No. Again, very confusing for students where they're like, oh, so can I encode? I've got an attribute. Can I encode that with area on my area mark? And the answer is, oh, no. Area is used up by the mark itself. It's not available. But then why is it called area? So there's a confusion point. But there's an even deeper problem here, which is that area is not the only channel in play, even though the name strongly implies that it is. So what's really going on with these marks? Let's go back to our friend, the Corplet maps. So what could we do to California? What if we wanted to encode something else? Could we size code? Could we shrink it? Could we grow it? No. It still needs to touch Nevada, not overlap Nevada. Could we translate it? No, can't put it on top of Texas. Could we rotate it? No, suddenly Southern California is including Nevada. Could we reshape it? No, California's not a beach ball. It's got its own shape. So why not? It's because there's actual meaning. That boundary means something. You can't just arbitrarily change it. The boundary is the data in some deep way. So also, if you start including these other marks, things would not go well. So I would argue that area mark is really not specific enough. On the other hand, area position orientation shape mark is a stupid name as well. So we don't want that either. So what might be a better name for this? Well, what about the idea that these marks are interlocking? What if we call these interlocking marks? So what I'm getting at with this is that a whole bunch of channels are all locked down together, in fact, interlocked. And the boundary is encoding a meaning. And you can't change the size or the shape or the position or the orientation, because what we're having is that the mark type is imposing constraints on how we can encode data with channels. So I saw some nods, but maybe I'm lying, because what about programs? I just told you we can't change California, but look at what these people have done. So what is going on here? I said you can't change California, but you can change them all at once. And in fact, that's what a cartogram is. That's a unified change of all the marks together to, in fact, keep some other constraints going. So interlocking marks are a global constraint. You can't change just one, but you could change them all simultaneously, and then you'll have a new encoding, and that's what a cartogram is. Usually we do this with a computer because life is finite, but in the old days, people did do this by hand. So computation is helpful, but not strictly speaking absolutely necessary for this kind of thing. Well, maybe this is just about geography. Could we do this with non-spatial data? And the obvious answer to this is tree maps. So we already talked through tree maps. We're using somehow containment to express parent-child relationships in the hierarchy, but also a tree map is encoding an additional attribute with size. So you're a size coding all these boxes in addition to using containment to represent children. Well, can I just take one of those boxes and make it bigger and shove it over in the corner? No, it would have just wrecked the treatment. So we have a very similar situation where you could recompute the thing completely, but you can't just change one. So it's the combined layout of all the marks put together, which is carrying meaning here. So the thing that's different from spatial data is that like that little box doesn't need something. But once I put, no, not what I wanted to. Right. So if the individual margins have no meaning, but combined together, they do have meaning. Somehow I lost the bullet point. I won't worry about it. Okay. All right. Here's another one of these quizzes. Let's go into these mark type. So this is a South China Morning Post graphic about fighting, about fights. So maybe it's a little hard to see from the back, so I'll blow that way up. So these marks, are they points? Are they lines? Are they areas? Are they some unholy combination of both or neither? So let's try to analyze these. So what kind is it? So if you'd asked me, say, 4 years ago, I would have said, is it a line mark? Well, no, it's not a line mark, even though it's tempting to call it a line mark, but they're not like it. You're not actually showing something blank. So is it a point mark that just happens to be a rectangle? So in 2020, I said yes, literally, on answer keys, 2 assignments. And well, so why isn't it an area mark? Well, area doesn't mean it. Shape doesn't mean anything, so why would it be an area mark? So in 2023, I've changed my mind and I've started saying no. You can't change the position, or suddenly you can't use the grid to look things up. You can't change the size, be on top of things or invisible. You can't reorient it or it would do the other thing. So this is something like those interlocking marks. So in fact, this is fully interlocking. The position are all locked down by the Indian choice. So what I now started doing that is that all tile heat maps are actually these interlocking area marks that you're using the grid as an index. You're able to use these positions to look things up. And size and shape and orientation are all equal as true, but they're also all locked down. You can't just change them arbitrarily without changing what's going on. So maybe these are like the image locking mirrors. Maybe this is the simplest possible case that helps us reason. And so, when you think about it, really as a pile heat map is a grid that's even more regular than a tree map, than a perblit map. There's that nice paper from Wood and Dykes that really talked about how you could go from a far-plus control map and try to observe, relative geographic locations. And you can sort of start to see the relationship between that and fully regularizing to a tile heat map. So somehow there seems to be some underlying structural similarities. So even though, you might think, well, but what's going on here? You're just color coding within the cell. So you're just indexing into that. And there's something really different about doing this than sticking a point mark inside of your cell and then doing things like size code the point mark. So this is the fire inspired by Bertin. And what you can see is that when you're just you have all these size coded point marks, but let's compare what you have at the top of size coded point marks to these color coded little cells inside the grid. I'm arguing you're doing something fundamentally different here. Okay, so let's go back to another example, circle packing. What the heck is going on here? So I would argue, although years ago I said they were size-coded point marks, now I think they're interlocking marks. That fundamentally, structurally, this is like a tree map scatter plot. Because let's think about what's happening. This is just an instance of a circle packing, this kind of plot. And so what's being encoded? Well, we're definitely using horizontal position to mean something. And we're using color in the same way we binned it into chunks. And so that's related with position. And yeah, we're size coding these things. But, well, what's free? Is vertical free? No. I mean, I guess you could motion code, but in fact, there's an unavailable channel, which is the vertical position is algorithmically used to avoid overlaps and minimize gaps. So the algorithm stole my channel. I can't use that for something else. So yeah, shape and orientation are equal, but they're not available. If I change them, I would need to redo the layout. If I suddenly changed every one of these circles into little rockets, I would need to redo the layout to make sure that I didn't have gaps or overlaps. So this too seems to be an example of interlocking marks. In fact, there's a lot of circle packings out there, like B-swarm plots. That's another example of a custom circle packing. If you don't try to make it B-swarm information, if you're just saying, hey, I want to pack my circles, you can do that into the algorithm here is you're trying to say no overlaps, minimal gaps, and the algorithm grabs position to do that layout. It's not available for encoding data. So speaking of cartograms, let's go back to that. What's going on here? Well, what we've done with the cartogram is we've special case circle packing where the geographic layout can inform where you put the circles. So this is just a specialized circle packing. And what we've done is we've thrown away the shape. We've regularized those boundaries with circles, but we're still size coding these points according to this other attribute. Okay, so while we're talking about cartograms and election maps, there's a lot of interesting cases. Let's look at a bunch of them. So here's some election maps where we're not encoding election data in the area. So I would argue these are interlocking. I mean, the static profiles we already talked through. And then we've got these two cases where we took all the states and we turn them into boxes or we turn them into circles. These are maps. And so the algorithms by the shape, but it's still grabbing all those other channels. So these are still interlocking. Can't just change one thing. What about these ones? Here's the election data. These are also interlocking. So what's interesting is that the contiguous cartogram, which is, often a little hard to see, people are typically much more excited about these unit maps that are somehow in space. The only way to understand these is to think of them at two different levels. At the top level, you've got something that's close to the boundary of a state, and they're definitely interlocking marks. But at the bottom level, you've got a bunch of little square boxes. These are little unit marks. So maybe these are unit marks. The only way to make sense of this is to think about the two different levels at once. At the top level, it's interlocking. At the bottom level, these are just little points. And you can actually get the countability of votes where you start directly counting those little boxes much more easily than trying to understand what's going on with the contiguous cartogram. Okay, am I saying it like thing is an interlocking mark? Is every circle you see an interlocking mark? Yeah, my answer is no. Sometimes we truly do have point marks, like a symbol map really is. And you stuck them with on the bottom with a label of points on top, and it's a symbol maps with the R point marks where you've got size equal points. So this idea that we have constraints and we think about marks through this lens. We've talked about these very highly constrained interlocking marks. Lots of channels are available. So I'm proposing that maybe we should call these area marks. What if we call them interlocking marks? What about the opposite, which is point marks? Well, they're actually unconstrained. You can do whatever you want to a point. You can encode more information with any of the channels that are available. So size or position or shape or orientation are the ones that we didn't talk about as being locked down before, like color or motion, anything is possible. Now you might wonder, do people sort of think circle when they think point? So maybe point's possibly a little misleading. What if we call them unconstrained instead? We make it clear that the interlocking marks are highly constrained. That might help us. So what about those line marks? Oh, let's rethink those too. So let us start with the basic question. Does a line chart use a line? It's like, okay, well, get a cup of coffee, sit down, it's an eggs table. Actually, not because what we're really doing is we're taking points and we're constructing connection marks between the points, and we're doing that to really give you a sense of trend because we're emphasizing the relationship between the data items. You may or may not actually draw points. Maybe you just make the lines without even drawing the points. You know, maybe smooth the lines. Okay, so we have like a paragraph long explanation for a line chart. So there's some deep way in which the line chart is not doing the same thing that we need when we say lines, when we think about bar charts or lollipop charts, we have a point and a line coming straight down. So what is going on here? The fundamental difference I now think is that line charts are encoding a whole bunch of items at once. It's not a single item. It is a mark that's representing actually all the items, not one, all. So whether it's piecewise linear or smooth, that you could think of that, well, that's a single mark. I could draw this without taking my pen off the paper, but it's showing items, not one item. So maybe we should really make this distinction, is that if you have a line segment showing a single data item versus somehow curved lines showing lots of items, maybe they should be the same thing. Maybe we should reason about them differently. And we should think about the part where you've just got a single mark showing a single item, let's call that a line segment. And the part where you've got these complicated things showing lots of items, what if we call these paths? So we can distinguish between segment and path. Maybe this one. Well, what about point marks? So what is the relationship between the length channel and the length of a line? Because I really wanted our vocabulary to align to this thing. So what's going on there? Is it just the same? Are they different? What is happening? So my fundamental question is, what is the difference between a line segment and a length-coded point mark? I think the answer is that they're the same thing. If they're the same thing, then how come I need a special name for them? So it's fundamentally, you can think of it as, the point markers in position and then length. Well, those are two numbers. And you can either think about the centroid where you put the point and then give it a length, or you can think about a max and a min height and some. But either way, you just have some way of representing numbers. So there's a strong similarity between length-coded point marks and line segments. So what if you put them together? What if there's a way, even when I draw pictures of, hey, here's a bunch of point marks, here's a bunch of line marks, that thing is the same. The thing in the red box is fundamentally the same between these. So maybe what's important is calling these singletons as opposed to multi-item. So speaking of area marks, when does a line mark turn into an area mark? If it's fat enough, how fat? Like where's the boundary? What if you show stuff inside a line? Is that an area mark? I'm not just color coding those lines. There's text in there. So what's going on here? How can we tell the difference between them? And moreover, well, hey, what about below the path? What if we fill that in? So now we start thinking about line charts versus filled area charts. So should we reason differently about boundaries of the line chart versus the interiors when we do a filled area chart. What is there an important difference between those and those? What's going on perceptually? We can see there's a lot more places to color in. Maybe we're more likely to see that color. Do we want to distinguish between these, and if so, how? Does it matter if you start stacking them? Like, what's stacked area charts versus a stream graph? You know, in the paper about stream graphs, they talk about how you can transform from a discrete set of stacked bar charts to this continuous stream graph. So, what matters here? Is what matters about is the interior? Is it discrete versus continuous? Does occlusion matter? Right? We had to think about the order in which we stacked these to actually see these stacked area charts, whereas we didn't really have to think about the order when we stacked line charts. So my current answer is, I think what matters the most is boundaries versus interiors. So I talked about this idea that we have paths, and maybe it really matters if the path is closed. And let's say that a closed path, call that a boundary. Maybe if it's infinite, like an infinite line that divides the plane in two, maybe that's also a boundary. And so if you've got a boundary, then you can talk about an interior. Maybe you might visually highlight the difference between the interior and the boundary, maybe you won't. But in any case, sort of by the act of closing that boundary up, you've defined it. And, we could fill that interior with a color or a texture or whatever we wanted. So what if the really salient and important thing here is not the fact that they have area, like all the other marks do? Maybe what's important is that there's a fill. So what if we called these fill marks? And then I would say that interlocking marks are a special case of the fill marks. So I've got this other way of thinking about mark types now, where I shove together the points and the line segments as being these singleton marks, whether we should call them singletons or unconstraints, maybe something to think about. And then there's these multi-item marks where you could have a path, special case of a path with boundary, or they could be filled. And all filled marks definitionally also have their own boundaries, and especially those interlocking. And then, we can still get into stuff I talked about before, like the connection marks for node-link graphs and the containment marks for the tree maps. Those are just special cases of paths, filled marks, respectively. So this is what we're emphasizing is, what does the mark represent? Is it a single item, or is it a bunch of items together? And that's the division instead of geometrically inspired point line area. So let's come back to the idea that I said, hey, we want to think about channels. When does using one channel constrain another? So is it because other channels are used? So in general, we have this idea that position is a really fine-grained way to, we need more than just position, right? Because notice that I was talking about things like rectilinear, which is high precision, versus, in depth, which actually is very perception of precision seen, and I really distinguish that from radial. So we need to at least be able to talk about these ways of laying out a whole bunch of marks together, and we need more than just the word position. So, but what you should notice is that at the same time, in the same way, you can't use them both at once. You could have made a choice, either use one or the other. So you can say not a horizontal and add a vertical to it. So vertical and horizontal each other, but somehow once you've committed to rectilinear, you can't cut over to radial. And I think what's going on here is that position is shared within a view. You can think of this as a global thing. And so if we go back to that sort of computer graphics way of thinking about this, then position is respect to a specific coordinate frame that's shared across marks. There's a shared set of axes. So there's a way in which position is shared, global, but like, what size? Well, one thing to notice is that, there's a relationship. If you've got area, then you can't separately code with length because you mix that up. And, likewise with volume. So, the larger ones assume the other ones. But in particular, and you can go from a length coding to an area, right? You could say, take a length coding and add a height coding. Whether it's a good idea is a separate question. Maybe it's not your best visual encoding, but it's possible. But what I want to notice is that there's the key thing about size is that it's global, as opposed to shared position. Size is global. And so that can be independent across marks, even though the shared coordinate system is shared. So when we think about position versus length, there's this way in which, we think a lot about aligned position, ultra high resolution way. of us being able to encode data. And it's because there's a reference frame. That axis is a reference frame, and we can make really small judgments. And in fact, even if you don't draw in the axes, you've got them for free because somewhere there's a window boundary, and we typically have rectangular windows, or there's like a display boundary of your projector. And so there's this way in which it's usually pretty unambiguous what the origin is. You can fight about whether it's the top left or bottom left, but there's not a lot to worry about there. Whereas these are just making judgments that are unaligned, and we are less good at that. And so typically, if you're using position prize your length coding, if at least you've got some sort of line mark, but not vice versa, right? You can have length without the position. So, here's one where instead of the bar chart where everything's aligned with the axis, you could say, oh, I could take these bars and make them different lengths. And then we can more easily read off the top max temperatures and the bottom min temperatures. It's harder now to read off the length, just the temperature difference, because we're trading those off. So what this map starts is these ways of dividing things up, where we notice that you've got an either or choice. You can pick for position, this is a shared coordinate frame, pick a rectilinear one or pick a radial one. But once you pick one, you can't go to the other in that same layer. You can also have parallel coordinates, but that's beyond the scope of this talk for Friday afternoon. Finish by 6:30 and let you go on a few lives. We'll talk about that. But what we will talk about is that then size is a look thing. You can independently of the shared coordinate frame size code things. You can independently orientation code a particular thing, even if you're in this larger shared coordinate frame of radial views. And then we've got some others that don't seem to have these dependencies. Color, of course, has 3 subunits within it. Hue, saturation, luminance. Again, that's another topic we'll get into today. Things like shape and motion are quite separate from these. So this idea that shared locks down local, but you can use local without shared, right? Once you've got this position coding, you're getting length coming along for the ride, but you could just length code without trying to communicate something with position. And similarly, if you've got angular position or radial encoding, then also you're using orientation, but you just separately use orientation. So there's this interesting distinction between shared coordinate frame and purely local choice when it comes to how you're including the marks. Finally, the one thing that we already alluded to is that multi-level analysis is important. We already talked about this idea of, that back to that example, Martini. Well, what's going on here? So literally, when we started having like, what is happening? And half the students said vertical position. Within the row, it's just previous to jitter inclusion. And then the other half of the students said, oh, vertical position. Because they were talking across the rows rather than within the row. So they're both correct, but you need both levels to be. So, back to the group bar chart that we saw before, well, what's being encoded? Clearly vertical position quantitative attributes. And yeah, we're redundantly using lengths to do the same thing here. And color means something. And so what's it's one thing, right? Within these bars, whether it's a purple or a red bar, that's what kind of things being done. But across the groups, it's what are the races? And so that is a different answer if you're thinking at the high level or the low level. And because it's rectilinear, you can't do radial, but and there's some other ones that are free, you can encode something else. So now actually coming back to this world where maybe it's useful to think it's not just marks. That once you start seeing an item, right, you can see, well, there's at some deep level a relationship between grouped bars and stacked, where you could move things around, transition from one to the other, or you could transition from multiple views of bar charts to a stacked bar chart. So there's sort of a way to go back and forth between multiple views, stacked bars, grouped bars, and maybe it's useful for us to not just think about the mark level. Maybe it's helpful to think about the glyph level. Maybe we should be thinking about Wilson channels, not just Merckson channels. And then maybe a larger set of visualization could be amenable to analysis using. So that's something to think about. And what about this idea of multi-scale interpretations, not separate views, but sort of within the view what's going on? And this is what led me to understand what the heck is going on with unit marks. So sometimes these are also talk about isotypes, unit encodings. So, here's one where there's a bunch of points, but position, they just try to shove
you're not encoding data with position. You're really just trying to count how many marks there are. That's what's going on with unit marks. Position, but sometimes it does. What's going on there is a multi-level interpretation. People often take these little unit marks and stack them together in ways that make it count, often with either lines or squares or rectangles. So that for one thing, you get the countability easier. You know, it's easier to count to 4 and 5 than to count to 20. So like at the top level here, there's an interlocking mark. There's all these messy squares about the regions that by wildfires and comparing them to the size of entire countries. So it helps with the counting, but at the bottom level, you've got a bunch of little unit marks and not counting, but you could actually color code those or hide these interactively, independently. And that gets us to that chart that flummoxed us at the beginning. Well, what's going on? Right? The answer is that's both a point mark at the low levels that you can individually color code in response to maybe a selection, and you've actually created then either lines or areas with these point marks. Or, you know, this example, which is you could actually start making bars out of little animal pictures. What's going on is a 2-level analysis where point marks have been combined together into a higher level problem. So it's Friday, we should declare victory soon. What I told you about is different models. The old models, there was this geometric mark model that goes all the way back to Bertin. There were these games based on these field tasks. And I'm wondering if there's other ways, categories of things that might help us think. So I talked about this idea of channel availability as a thing to consider about a different model that's very much based on constraints. With these unconstrained or singleton single items, and then there's paths and filled lots, and interlocking is a special case of filled. I've even started thinking about this idea of shared versus local as maybe a way to help us categorize channels and usefully think about what's available and what's not. And it's the idea that we really probably want to think about marks at more than one level, whatever we have as visual encoding. So do these help us think about the design components? So far they've helped me some. I'm pondering whether I can get this to be concrete enough to actually be a full-fledged model of things. And so what I'd love is to get questions, to get answers, to get thoughts, to debate. So thank you very much for your attention on a beautiful Friday afternoon.